We're Driv3n. As part of the Robotics, Science and Systems class at MIT, we've been working on a custom race car platform to complete various autonomous driving challenges. The race car platform itself is equipped with a Velodyne LiDAR, a Z depth sensor, and an inertial measurement unit, or IMU.
Our final challenge for the semester was the Labyrinth Challenge. The objective of this challenge was to navigate a specified distance away from the race car's initial position through a maze of randomly placed obstacles, with no prior knowledge of the environment, while avoiding collisions. We divided the task into 4 main objectives: simultaneous localization and mapping, or SLAM, path planning, waypoint identification, and trajectory tracking.
The first objective of this challenge was to generate and continuously update a map of the race car's environment using SLAM. This allowed the race car to determine its position and orientation in an unknown environment. Due to the challenge of developing a reliable SLAM algorithm, we used an optimized ROS implementation of Google Cartographer for SLAM on the race car platform. We verified the performance of this implementation by qualitatively comparing maps generated on our race car, shown here on the left, to the actual floor plan of the environment, shown on the right. The color gradients used by Cartographer when depicting the map environment were used later on to identify free space, obstacles, and regions of interest.
Our next objective was to develop a path planning algorithm to generate feasible trajectories for reaching possible exit points. We chose a rapidly exploring random tree, or RRT, algorithm, visualized in yellow here, because of its ability to quickly plan paths in narrow environments. However, modifications to our RRT implementation were made to ensure the dynamics of the race car allowed for accurate execution. After generating a successful trajectory, the path was modified using Dubin's curves. In order to implement a more accurate trajectory tracking algorithm, the final trajectory stored pose and steering angle information with each point, in addition to absolute coordinates.
In order to identify potential goal points for escaping the maze, regions of interest were located using occupancy probability data obtained from the Cartographer map. From these several points of interest, labeled here with blue dots, a single point of interest was selected based on its relative position and orientation to the race car. In the event the race car's planned path intersected an obstacle, a new waypoint would be selected in order to initiate path replanning toward the maze exit. Each trajectory would terminate outside the escape circle to ensure challenge completion.
The final piece of the challenge was to design a trajectory tracking controller that allowed the car to closely follow, both forwards and backwards, a given path. We implemented a follow the past algorithm, which uses pose and steering information provided by the trajectory, in addition to pure pursuit, to ensure accurate trajectory tracking. After combining the components of the challenge, we tested our maze solver on a real labyrinth. In the top left visualization, the predefined escape radius is shown as a large yellow circle. The goal point selected by RRT is represented by the purple circle, and the forwards and backwards trajectories selected by RRT are shown in green and red, respectively. The car was able to successfully map, locate points of interest, plan a path, and follow that path to safely exit the labyrinth.